Hey guys, welcome. Yeah, so before watching this video, you should watch my first three videos on Laurent series. That's the intro, and then examples 1 and 2. This video naturally follows those three videos in that order. Yeah, cool. Now, as it says, we're gonna do integrals using Laurent series. So in this video, we're gonna be able to see what Laurent series have to do with doing complex integration. But it's not hard to see because, well, this is the Laurent series defined on an annulus, and we saw in the intro video that the coefficients, the c sub n's, end up being this right hand side, which is an integral. In fact, if we multiply both sides of this by 2 pi I, then the integral is isolated, and so then you see like kind of how we can go about using the c sub n's to do integrals, right? Okay, cool. Now, in the intro video to Laurent series, we specifically said that one of the coefficients is very important, and that's the coefficient corresponding to n equals -1, c sub -1, right? And in fact, we had it designated with the name residue of f of z, right? Like, well, let's see why this c sub -1 is like a really useful coefficient to know. First of all, I'm going to provide you two examples a little later in this video, and in the second of those two, it will be very clear how we'd go about using the c sub -1 coefficient. But when n is equal to -1, look at this. On the left, we're going to get c sub -1 equals 1 over 2 pi I times, well, the integrand is going to be, well, in the denominator, this here is going to be raised to -1 plus 1. That's to the 0th. So in the denominator, we're just going to get a 1. And so the integrand is just f of a dA. And multiplying both sides by 2 pi I, we're going to see that the integral over c of f of a dA is 2 pi I times c sub -1. And so, yes, that's why this c sub -1 coefficient in the Laurent series expansion of f is such a useful thing to know. All right, now again, we will do this slowly, but like first, let's just in general show why the c sub n's are important, not just the c sub -1, but the c sub n's period. Because, well, if we were to do this integral, right, like first, let's make it abundantly clear that this integral looks very much like this, right, by doing this. Now, the fact that I switched from z to a, not important. That's just a variable change. But otherwise, this z cubed, which I can write as z minus 0 to the 2 plus 1, well, again, I've switched from z to a, but that's exactly what I said right here. Z minus 0 to the 2 plus 1. That's exactly what this is, right? Okay. Cool. But then looking at this, it's easy to associate it to this now. Because, well, first, we see that n is equal to 2, right? And so then what we want is to say that this is equal to 2 pi I times c sub 2. That's where we're headed, right? So this implies that now we can say that this here, which is of this form, is equal to 2 pi I times c sub 2. Again, c sub 2 because n is 2. Looking at this, right, and comparing it to that, I can see that n is 2. Otherwise, f of z is e to the z, and so if I so chose, I can call it f of a, and it'd be e to the a, right? And so then the c sub 2 here that we're talking about is the c sub 2 coefficient, or the c2 coefficient if you want to call it that, and the Laurent series expansion. That's the one associated to the z squared term, or the a squared term if we're using the variable a as opposed to z. This is what I'm saying. C sub 2 is just a coefficient of the z squared term and the Laurent series expansion for f. And f again here is e to the z, right? And e to the z has a simple Laurent series expansion. It's this, and the z squared coefficient, as we can see here, that is c sub 2, is equal to 1 over 2 factorial. So c sub 2 is 1 over 2 factorial, and that's just 1/2. And so we come back to this equation here, and we see that the left-hand side, this integral, is equal to 2 pi I times c sub 2, where we know now c sub 2 is 1/2, and so I've replaced c sub 2 with 1/2. And so that all simplifies to pi times I. But wait, this here is equal to this here, which is the same as this here, and therefore that means that we have solved this first integral, which is our integral has value pi times I. Cool. And so then on to our second example. And this is the second example. And again, we want to do this using this here, right? The C sub n's. And we see immediately that this denominator isn't present here, which means that we are working with n equals -1. And so we know that the Laurent series expansion for e to the 1 over z is simply found by taking the expansion for e to the z and manipulating it much in the same way as we had done in calculus when, we got new series out of old ones by modifying them. And so then, if we simplify this, it's easy to see that we could write it this way. Now, the c sub -1 coefficient is the one associated to 1 over z to the first. So in this writing, it's the one associated to n equals 1, because when n is equal to 1, we get 1 over z to the first, but that's really z to the -1, right? Okay. All right. So we do this, right? And this is just a term-by-term writing of what I already had here. This here and this here are the same, and they're both equal to this. And as we said, it's this guy that is of importance to us, in particular the coefficient there. So, I'm just saying let's recall now this so that I could show you how this integral and this are the same. But what I had before and what I just displayed are identical. It's just like making it very fresh. Yeah, okay. So this here, so we recall the coefficients are defined this way in the Laurent series expansion. And so c sub -1 in particular is going to be this, right? And so that wipes out the denominator. And so then we see that c sub -1 is equal to this here. Well, I'm just showing maybe too clearly how the algebra worked out so that the denominator is wiped out. But obviously this simplifies to just this. Right? Okay. But c sub -1, right, as we said, is the coefficient of this fella. And so that's 1 over 1 factorial. And that's just 1, right? And so c sub -1 is 1 means that this now could be written like this. And upon multiplying both sides by 2 pi I, we see that the integral over c of f is equal to 2 pi I. But f in this case is e to the 1 over z, right? And or e to the 1 over 8, doesn't matter, and therefore that means that the integral of this here is equal to 2 pi I. Yeah, cool. All right, I see. I do. I hope you see how Laurent series have to do with integrals, and soon enough we're going to be doing lots of integrals. So if you like complex integration as much as I do, the future should be bright. The immediate future. Okay, all right. Keep watching. Take care.